Okay. Chapter 4 does talk about cell arrays and structures, which are different ways of storing data in Matlab. With a standard command like this, I'm generating a matrix. Over here, I see that the matrix is a 10 by 10 double. You could, right, thank you, yeah. It's only got one kind of data. You can't put character strings in A, and so on. So we there are different data structures that help you do that. They are the struct and the cell array. The struct, okay, let's see. Got to find, there we go. Open up my file here. Computer. Okay. This is how you create a structure. You'll notice you use this command, struct. This is, structures are fields and data. So you give a structure field data pairs. So the field is course. The data into the first element of the structure is this, is our course name. Student, I picked the A's out of our student population. So students is the second field. Also, Brooke is the second data point. Scores is the third field. Now, I intentionally, okay, we have characters here. We have characters here for data. We have a matrix here. You can put different kinds of data into structures. One field can be string, another can be integers, another can be doubles, another can be matrices. Yes. Well, let's let me create the two structures. I'm going to go ahead and run the section here. So I'm creating two rows in the structure, if you will. So let's run it. Run section. Now we got this structure. Double click it and double click this. So the values contained, this is the field name, fields, there we go, fields right here. These are the values in the fields. That's for the first record of the structure. Let's go back to the structure, double click the second element in the structure, and we have the same course name but a different student with different scores. Field name, values. Let's go back to the generating functions. Field name, value. Field name, value. Field name, third value. Second row, second element in this structure, SEM grade structure. Okay. This time, you just select a row of the structure. Let's say, here's the second row. You just select it like this. That'll pick out the second row. And let me close this so you can see better. There we go. So the first row, I can create more rows too to the structure. I can create more fields. So field name, data. Field name, data. You can mix data in a structure. Strings, matrices, doubles, integers, things. Different fields can have different kinds of data. Matrices can't. You're limited to one kind of data with a matrix. You can put about anything you want to in a structure. The advantage of a structure is that this is like a database. Your SQL databases, Microsoft Access and things like that, that's how databases are organized. They have fields and values. They're organized like a table. And for each field, you can have a different type of data in each field. So structures are pretty good um, for handling database data. Let's do.
Engineer 2304, would that be a separate map file?
No, it's an element in the structure.
What is the data for 2304?
I created it here. So this is the first row of the structure.
Right, because you have field as in data. Well,
Second field. Okay. Let's do this. Third. So we're going to create.
Yeah, where did you create the field? In the here or in the script?
Here. Or hey, you can put this command in a script. It doesn't matter. I'm going to create a new row. And your grades are lousy. There. So I'm going to create a third element in this structure. Oops, hit return. There we go. And that's what's in the third element in this structure. Here's what's in the second element.
so the scores is the data for the field nickels. Is that correct?
Nickels is data. Scores is a field. So you have field name, data,
Right.
field name, data, field name, data.
So you don't even have to put the apostrophe in the data, right?
Well, yeah, I mean, that's just
No, because
It comes out because it comes out with.
Yeah, with the apostrophe, so you don't even have to put the apostrophe.
Field name, right. Here you have to use the apostrophes. A string field name, string data. String field name, second field,
You're saying like in the data you don't need it, do you?
string data.
So there's no actual.
Oh, you mean here?
No, like on
The
ad hoc.
second one, because it comes out with the.
Because it comes out with the apostrophes in the.
Oh, when you print it out,
Yeah.
like this, yeah.
Can you make it without that?
Basically, no. It's now if you use this data. Let's do this. These are characters. This, okay, put a period here. I can pick out the course now. So this is the first row. This is the course field. And I print it out. I do that and get, well, now you get an answer which does not have the apostrophes, you'll notice. Okay? So this is how you can pick out the data. If you don't put the period course or the period field name, you'll just get all fields. If you put period field name, you'll get this. We can even go one step further. 3. What should this produce? So this is the first row. This is the course field, and this is element 3, just like elements in matrices. Elements in string matrices. Who knows? Who has an idea what this will produce? No.
No, I got you. It's going to be student physics 2425.
It should be engineer 2304 with the scores.
It will pick out So now you know how to. This is the basics of structures. I'm going to go to cell arrays next, unless anybody has any questions. So I'm picking out the scores field that gives me the number 85. First element in the scores field, 85. Okay, that's all I wanted to say about structures. A lot of time, well, when you're dealing with numbers primarily, you'll just deal with matrices. But if you have some database computer geek says, here's my database data, now you know what to do with it. Okay. Yes, it is. And it's probably not advisable. There's better tools. Yeah, well, let's go to Excel. That's a good one. A cell array is really good for things like Excel spreadsheets. So I put up spacely sprockets. When you import a spreadsheet, you have choices. You can have 5 different vectors. This name, this name, this name, this name, and this name. This you can change the target type. I can make it a oh, it's making it a cell anyway. This particular column, it's making it a cell anyway, and I don't have a choice. I can't make it a string. Okay. This one, because the way strings are handled in Matlab, each character is an element of a character array. Well, you'd have to put you'd have to play around a bit to get it to work well as a string array. Okay, so and then this one will just import vectors. This will import matrices. Here's an import called a cell array, and I'm going to select everything. What it will do is it'll create a cell array called spacely sprockets. A cell array is another way to organize different kinds of data. So I have characters, I have row headings, things like that. So let's import it. It's got all this data in it. Let's import it. A cell array works well with Excel spreadsheets, cells. It's kind of built to work well with cells. You'll notice you don't have a choice to import a structure here, but you do have a choice to import it as a cell array. So let's import that, and I can close my import window now. I have spacely sprockets. And the way a cell array works is you use the curly braces. So structures, you just use ordinary parentheses. Matrices, use the square brackets. Cell arrays, the curly brackets. Okay. The first row of that cell array. And, oh no, that's the very first element. It's not just the first row, because there's rows and columns. Let's see. All columns. So first row, all columns. Just like when you specify it in matrices, the colon gives you all the columns. So now I'm getting all the columns. So the first row was, let's go look at spacely sprockets again. There we go. Pull it up in Excel. So the first row was a blank in the first column, Q1, Q2, Q3, and Q4. I imported it from Excel. So here's the Excel spreadsheet. Here's the first row of that spreadsheet. The way you select the first row, all columns, is just like a matrix. You could select columns. You could do the selections just like you work with matrices.
What would the first column look like?
Let's try it.
Because you said it was not a string, so it
There we go. First column.
Oh, so it does come out with the, oh, yeah, with the name.
Right. Yeah. So this is a way to handle, okay, Excel spreadsheets. If I just do the whole thing, it'll give me a whole bunch of stuff out. There we go. It organize, if it can, it will organize it like the Excel spreadsheet that I imported. And we have different kinds of numbers. You see how we can select out data in a particular cell in this fashion. Okay, so that's about all I wanted to say about cell arrays and structures. You could keep going. Let's do one more thing. Let's make row 2, column 1 a vector. So spacely sprockets of row 2, column 1, and equals this vector. Oops. It gives me a warning because I put a brace in without a beginning brace. Okay. And now it's telling me, oops, I didn't want to replace spacely. I dumped spacely. I accidentally dumped spacely. I replaced that character string with a string array. So to see what it looks like, there we go. There's your vector. You can keep going. Element number. Yes, you could. I could put spacely back into it. So a cell array, you can put any kind of data you want to in the cell. Now, what this will do is it will take the 4th element in that cell, which should be 4. There. Okay, that's cell arrays and that's structures. Let's and I went and have it in my editor. There's my editor. Okay. Now, differential equations. We're going to solve, like I said, we're going to do some simple ones. Population growth. The first one is population growth. Which is kind of, even if you haven't had calculus, it's kind of easy to understand. That in any given year, the change in population is going to equal some constant times the population times how much time has elapsed, right? The rate you're making babies times the time, and that's proportional to the population. It's the rate. You have twice the population, you're going to have twice as many babies. 3 times as many babies, and so forth. So the number of babies made is proportional to the population. What kind of behavior is this? Mathematically. It's definitely human. What do we, population? What kind of? How does exponential? Population, exponential growth. So what you do, let's go look at so I'm going to go ahead and run this. But first of all, we have to look what's in the function dp. You'll notice I did ordinary differential equations, routine 23. I did it 2 ways. I gave it a function handle here. And the second time I did it, I just named the function here. So you could do it either way. This is just to show you can do it either way. Here's how it works. Let's see. Let's go see the function. And the first function was dp, which is how the population's changing. What the ODE 23 needs a function where the derivative is coming out. That's the delta P is coming out. So I call it dP out. What goes in is time and current population. And I'm just putting this K equals 1. That the change in population coming is equal to the population. So that's my function, real simple function. We expect an exponential behavior. Now let's go to, let's run it. Now, so here's my function. The derivative coming out, it has two parameters going in, time and population. Two parameters going in. This is the range in time that it will use. And now I forgot what that one is. I forgot what, I'm going to do a help. There's several, as soon as I do help, it's going to give me a lot of other differential equation solvers. You've got lots of functions that can do this. There are different algorithms. Some of them might be better for some problems than others. So that's why there's so many. That if ODE 23 doesn't work, ODE stands for ordinary differential equations. If ODE 23 doesn't work, then you could try ODE 45, or you could try these other algorithms. They're just different algorithms. They're different numerical algorithms. So if you have a problem that you can't solve with one, you can switch to another and try it. So you can keep going with your problem until you get there. So going way back to the top, I need time out, y variable out. Oh, 1. I remember now. You give it the function, you give it the span in the t variable, in the time variable. I'm using time, just like this help routine is using time. And this is where you start. I'll show you. Here's time span. 0 to 10. Yeah, here's dP. Here's what dP looks like. Okay. I didn't have to. I just wanted to show it as an example. You can use a handle. P is population, T is time. I mean P for population, T for time. dP is a change in population. Okay. Delta P. Okay. So it needs a function in this form, and this is the range of the time variables, the x variable. Right. This is pretty generic, so it's seconds, years, milliseconds, whatever. Right. Right. It needs a starting point. It's the mathematical function needs a starting point. It's doing a solution, so it needs to know where to start to try to generate the solutions. It's like F0, function 0. You guys have seen that before. If you try to find where the 0 of the function is, if the zeros are 2 and -2, if you type 3 as your initial starting point, it'll find the 0 at 2. If you type -3 as your starting point, it'll find the 0 at -2. So that's kind of what you're starting. You're starting your search for a solution at y equals 1. It's going to generate it automatically, although the function lets you have some control over that. So when you go into the help system, you see all the details about the function. It will give you some control over the values of t and p. I'm going to suppress output because when I run ODE23, it will generate the time. It'll generate a time vector, and it'll solve the equation and generate the population vector. I'm not going to spit it out on the screen. I'm going to plot it. So that's what the plot command is all about. And I used a handle here. I just realized I don't need the first line at all. I can comment it out. It ought to be just fine. So let's go ahead. Yeah, I created, I'm using the handle generator right here. I don't need to generate a handle here. I goofed. Okay. Run section. And let's see what it did for us. There we go. There's the plot. Exponential, just like you expect. Right. There we go. This is the range.
Yeah, what does that have to do with HDP?
This, it doesn't.
Nothing.
Nothing. I just commented it out. I goofed. I created a handle and then I didn't use it. I don't need it. I commented it out. The routine ran fine.
So where is it getting P at?
It generates it. It solves for P. It solves for P. Yeah, I can. That's some of the power of what this thing is really good for. You could give it a really crazy differential equation, and it would, and it solves for it. The harmonic oscillator, I'm going to do a simple harmonic oscillator. I might do the complicated one in just a second, if we have time. I'm going to go to the second example of how to use ordinary differential equations. This one, okay, we're done with the first order. Setting up a second order is a little more complicated. What you have to do, so harmonic is the name of the function, and I'm giving it the ranges, and you'll notice you have a vector now. Instead of a scalar, you've got a vector because you have, let's go see the harmonic function. Okay. So this is the change in x. You guys remember from your physics that velocity is the change in x over change in t. And you guys are studying. How many of you have, has anybody not seen this in 24-25 or calculus? If you've had calculus, you're okay. If you've had 24-25, you're okay. Who has not seen this? Anybody not seen this? So everybody has seen it. You're at least at the 24-25 level. If you're not, raise your hand.
What's the 24-25?
Physics, 24-25, university physics. Okay. Have you had calculus?
Yes.
Okay, so you're okay. If you've had calculus, or if you're enrolled now in physics 24-25, what I'm about to present should not be unusual for you. I'm asking if there's anybody in this audience who has not had either calculus or is not currently enrolled or who has not yet had physics 24-25. Anybody in that? So Zach, what have you had? Pre-calculus? Are you in calculus now? Okay. So you should be okay. I think you'll understand this. Okay. So, velocity is the derivative of x with respect to time. Acceleration is the derivative of velocity with respect to time. In this, we are going to call this is the second element of x. This is the derivative. By the way, in physics, a lot of times the derivatives, we put a dot over the variable. That means the derivative with respect to time. So that's why I called it x dot. So the second I need to calculate derivatives. For this function, I need to calculate, or I need to say the derivative equals this. And
Why is it square, or why is it 2 to the second?
because it's a derivative of velocity. Oops. So the derivative of x is first, and then the derivative of the velocity is number 2. So this is the way to do second order equations. I'm just showing you how to do second order equations, how to set them up. So it calculates the, it's going to calculate the a vector that the second element of the vector, the second column, by the way, you'll notice it's a column vector. Oops, yeah, it'll be a column vector. The second column is the first derivative. The second derivative is going to be equal to, this is the equation. This is how the equation works.
On x dot 2, is that x in respect to 1 or negative x respect to 1?
Okay.
Is that correct?
Um,
It's on the bottom line.
negative. Negative. So,
Negative x to respect to 1, correct?
right. The second derivative of x this is how harmonic oscillators work. This is a spring. The frequency, this is angular, omega is angular frequency, and I'm taking omega equals 1 for this example. You'll notice that I don't have negative omega squared times x1. I'm just taking omega squared equal 1. I'm trying to simplify the example, in other words. So this is the harmonic oscillator. You have a, let's see, I have my slinky around here somewhere. Okay. So the force, I stretch my slinky. The force is proportional, by Hooke's law, the force is proportional to how much I stretch it. And it wiggles up and down. It oscillates up and down. So that's why if you've had physics, you should understand this, at least the basics and beginnings. And if you had calculus, or you're in the middle of calculus, you can understand this sum. Okay. So we're setting up a second order equation. You have to use key headline. Before we use scalars, the first order equation we use scalars. We have to use vectors for this, and it expects this kind of output. It says the first derivative is just going to be equal to the second element of my displacement vector, which equals velocity. The second derivative is this equation. Okay, so that's my function, and I get this vector out. I still have to put in my variables just like before. The time is the first variable, the displacement's the second variable, just like before. And I go back here. Now I can run it. This is the starting, so I'm going to pluck it. That the displacement is 1, the velocity is 0, x2 is 0.
The bracket on that on the harmonic function, I think you missed the bracket on it.
I don't think, let's see, I didn't think so.
On the second line? Oh, okay.
Okay. Okay. So, function name, range of time values, and initial conditions, where you start the x. I'm going to pluck it. I should come up with a cosine wave. We know the solution to a harmonic oscillator is a cosine. Again, I'm not going to output the numbers. I'm going to plot them. And let's run the section. And it should pop up with a plot pretty soon. it doesn't, I can go over there and see what the plot looks like. There we go. Yeah. So this is, okay, this is time to end. You've got about 5 minutes left in class. I'll go ahead and end here. This is how to set up a first-order differential equation and how to set up a second-order differential equation. And, okay, any questions? If there's no questions,